Hello everyone, in this lecture of dynamics of the lithosphere, we will discuss about channelized flow solutions. So this is the fourth part of the lecture series on viscosity. So to provide quantitative estimations of viscous creep in geodynamic system, we in fact need to consider the force balance, as we did when we were studying the effect of flexure on plates. So this is a little sketch that shows you a subduction system below a continent with a growing arc and shows you the direction of motions. And obviously, when plates are moving past, they are inducing a drag below, which deforms the material beneath the plate. So the force balance is stated like this. So we have rho times dv dt. This is the inertial term. We have the gradient of the deviatoric stress minus the gradient of pressure, because we have made the split between deviatoric and volumetric deformations here. And we have contribution from the body force exerted by gravity. Over geological timescales, accelerations of plates are negligible, so it means there's an insignificant role of inertia. We will make the assumption that this term is zero. So we end up with the Stokes equation. Again, we have the gradient of the deviatoric stress tensor, the gradient of pressure, which is subtracted, and rho g, the body force. Now, we make a second assumption, is that at high temperature, the viscosity of rocks is relatively, still huge, relatively low, 10 to the 17 to 10 to 21 Pascal times seconds. Over the geological timescales, the rock may be considered as creeping incompressible fluids, and we will neglect the effect of elasticity and volumetric deformation. So this is the rheological constitutive law they want to use that relates deviatoric stress to deviatoric strain rate with a viscosity coefficient eta. Further, we will make an important assumption here. We will assume that the viscosity is constant with space. So the viscosity flies out of the derivative of stress. This is an important assumption which will be relaxed later in the lecture. So we end up with this equation. See the body force term as left to the right hand side now. And we will insert the definition of the deviatoric strain rate, which you may remember from a few lectures before. Epsilon dot ij prime is 1/2 of dvy dxj plus dvj dxy. So let's use this expression and substitute it into the Stokes equation for constant viscosity, and you will obtain this equation now. So you see eta is a factor of a sum of second order derivatives of the velocity vector components with regard to the coordinates. This term here comes from the normal stress. This term here also comes from the normal stress, and the other terms here and there are coming from the cross derivatives from the shear stress gradient. So these equations are only valid for the constant viscosity assumption. So why do we bother with this? There are a lot of viscous flow problems in geodynamics and lithosphere dynamics. One example here is the exhumation of high-grade rocks. So for example, the high Himalayan series in the India-Asia collision, you see different types of models. In each model, you have the Tibet here in blue and the Indian plate being subducted with this color here. And at the interface, things happen. So this plate is definitely moving below in all of the models. And there are different behaviors of these red units. And all of these models, they are showing different modes of viscous flow and exhumation of the unit. In addition, in these models, you see an interaction. Here you see a lot of clouds. So this is basically representing erosion due to precipitation on the front here, which would, in addition, increase the pressure gradient that may pump the viscous units upwards. If you consider the exhumation of subducted crust at a plate interface, so inside subduction zones, there are also different models, and all these models, A, B, C, or D, they all involve a moving footwall, so there's a plate moving down, but they also involve different types of pressure gradient, which will also drive the flow. So you will have pressure gradients inside the channel, which may cause a return flow of subducting unit in a subduction channel. Another example would be the motion of the lithosphere on top of the astenosphere. So if the plate moves with a given velocity, it will shear the astenosphere below. So there is a flow which is induced by the motion of the plate, but there may also be pressure gradient in the astenosphere that drives a large scale mantle flow, and these two viscous flow may interact together to trigger counterflow profiles. Another example would be the flow of a glacier down the slope of a mountain. So you would have a glacier represented by this slab here. It is on a slope with a given angle alpha, and it may flow under gravity along the slope of the mountain. So these are all examples of viscous flow problems in geodynamics. Now we go back to the equations and we will introduce first solution, which is the Couette flow. So this model was introduced by Maurice Couette, which you see on the left hand side, and it is designed to study the flow in a channel which is induced by the motion of one of the walls. So we have X horizontal, Y vertical. In this channel, you see that the vertical component of velocity varies with the Y coordinate. So we need to go back to this equation and find which term provides us with a vertical variation of the X component of velocity. So we check out these terms here and we look for the one that expresses a variation of Vx with Y. It is not this term, it is not this term, it is not this term, this one neither, this one neither. The focus goes to this term, which is the second derivative of Vx with regard to Y. So we will keep only this equation and we will make additional assumptions. First, that there is no pressure gradient along the channel. So we remove this term. Then there is no horizontal variation of X along the X axis. So Vx does not vary. And there is no component of Vy. So Vy is simply 0 everywhere. Only Vx varies with Y. Then we assume that the gravity is vertical, so there is no horizontal, or there is a 0 component of G. So this term also vanishes. So we end up with this equation, and if we look now for Vx, we obviously need to integrate this equation twice, so let's do it. We do a first integration with regard to y, and since the right hand side is equal to 0, the first integration gives us a constant a on the right hand side and drops the order of the derivative by 1 on the left hand side. Let's integrate again. Now we obtain Vx times eta on the left hand side, and we obtain a times y plus the second constant b on the right hand side. So we obtain now a generic solution for Vx, and we want to make this solution specific by applying boundary conditions. So let's assume this. Vx is equal to a value of 0 here at the base, or a value specified as Vs, S standing for south, and Vx is equal to V north at the coordinate y equal h at the top of the channel here. By using these two boundary conditions, one can obtain the value of a and b, which are listed here. So this gives us a full solution for the Couette flow problem given these two kinematic boundary conditions. So the solution of the Couette flow, it's a solution for the flow driven by plate motion. So for example, the motion of this wall here. It provides us with a linear function for the velocity. In turn, the stress is constant inside the channel because it's linked to the first derivative of a linear function. Let's have a look at a second model, which is called the Poiseuille flow, which was introduced by Jean-Léonard Marie Poiseuille, which you can see on the left picture. So this model is designed to study the flow inside a conduit, but a flow which is induced by a pressure gradient along the conduit. So there will be a non-zero pressure gradient along the conduit. This pressure gradient is along the x direction in our sketch. Again, we observe it is the Vx component of velocity that varies with y. So let's identify the term of interest. It is not in the second component of the Stokes equation, but in the first. Vx varies with y in this term here. And dp, dx, the driving term, is also present in this equation. So we will simply cross out the terms as before, because Vy is 0 and Vx does not vary with x, and gravity is vertical, so we get rid of this term. Now we have this equation, and you should notice an important difference with the previous example, with the Couette flow example. The right hand side here is not 0, but it's dp dx. So let's integrate this equation twice. First integration leads to a drop of the order of the derivative on the left hand side and leads to the appearance of y as a multiplier to dp dx and the first constant a. The second integration leads to y squared divided by 2 as a multiplier to dp dx on the right hand side and the appearance of a linear term and a second constant b. So if we solve for the velocity, we obtain this expression, which has 1 over viscosity times a term which includes a second order function of the coordinate y. So that's a general solution, and again we want to make this solution specific for our problem, and here we will assume that Vx and Vy are 0 at the top and bottom of the conduit. So by using this boundary condition, one can determine two constant, b being 0, so that's a trivial one, and a is minus dp dx times h divided by 2, where h is the thickness of the channel. So this Poiseuille flow solution, it allows to describe the flow which is driven by a pressure gradient. You see that the solution for the velocity is quadratic with y, so the velocity profile is quadratic. As a result, since the stress is proportional to the first derivative of a quadratic function, we will obtain a linear stress profile in the channel. So we have derived two simple viscous flow solutions in channels, and the question is, can these solutions be derived for more complex or more realistic rheology? In particular, a couple of lectures before, we've learned about the power law rheology, which was essential to describe the behavior of rocks. So in this power law rheology, there was a special effect, is that the effective viscosity, if n was larger than 1, it varies with the strain rate. So this is how we express the power law relation. Strain rate is equal to C times stress to the power n. And the resulting effective viscosity is a function of the strain rate or stress and the fitting parameter C and n. So the answer to this question, can such solution be applied to this case, is yes. But now we expect the effective viscosity, the slope, the local slope of this line, to vary with the strain rate. But also the strain rate in our channels will vary with space, especially in the case of the Poiseuille flow. So we should expect that the effective viscosity will vary with space. So we need to go back to our first assumptions. So we go back to the Stokes equation, and with the power law rheology, the viscosity will not be constant with space. So we are not allowed to use the assumption of constant viscosity we have made earlier on. We should not apply this simplification. So let's expand as much as we can this equation here. So we get the x and the y component of the Stokes equation. So that's the stress gradient which is being expressed here, and the pressure gradient. The viscosity is allowed to vary spatially, so we will not be able to take it out of the derivative. Now we select a different configuration. We make a channel to study Poiseuille flow. Now the channel is oriented vertically. So it's the y component of the velocity that varies with x. So let's look at our equations. We have a vertical conduit with flow inside. Vy varies with x, and tau xy will vary linearly with x. Which equation do we select? We are looking for a variation of tau xy with x, so it's definitely not in this component of the Stokes equation, but we should rather look in the second one. We have this term d tau xy dx, and that's the term we want to select. So we reduce this equation to a horizontal derivative of tau xy. It's equal to dp dy minus rho gy. So we have this equation, and we want to integrate it to obtain an expression for tau xy. So let's integrate once. Since the right hand side is not 0, x appears here and the first constant appears. It is A. Then we will substitute the power law relation. So the stress will be equal to epsilon xy divided by c to the power 1 over n. That's how the left-hand side is being modified. Now, let's solve for epsilon xy. So we simply take the right-hand side to the power n, and we multiply it by the constant c. Now we use the definition of shear strain rate, which is 1/2 of dvy dx plus dvx dy, which is 0. So we introduce dvy dx in this equation, and the factor 2 comes to the right-hand side. Finally, we want to integrate this equation to obtain Vy. So we need to perform a second integration along coordinate x. And to reach this point, we need to identify that the primitive of this term here that features x with a power n can be expressed this way. This can be checked algebraically. So the final expression looks like this, and this is again a generic solution which we want to make specific. So to make this solution specific, we will assume that tau xy is equal to 0 in the middle of the channel. So for x is equal to L divided by 2. So if we do this, we can obtain the first constant A, which is equal minus L divided by 2 times dp dy minus rho gy. Then we apply the second boundary condition, and the second boundary condition states that Vy is equal to Vy0, which will be 0 in our case, for x equals 0 or x equal L. This will give us the second constant B, which is expressed this way. And we get finally an expression for the flow driven by pressure gradients in a vertical conduit. And this model accounts for variable viscosity, it accounts for power law creep, and can also additionally account for gravity. So that's an extended Poiseuille flow model, a nonlinear model. So it's possible to derive flow solutions for more complex rheology, as we've learned previously in the lectures. So as a conclusion, in the viscous crust and mantle, the flow may develop as a channelized flow. The flow can be driven by the motion of a plate, that's called a Couette flow. The flow can be driven by a pressure gradient. In this case, it's a Poiseuille flow. And of course, the flow can be mixed between these two enders. In addition, solutions can be derived in order to account for the effect of complex rheology. So we've seen the example of a power law Poiseuille flow model just previously. So as a general conclusion to the lectures on viscosity, I think we saw that permanent deformation, inelastic deformation, and time-dependent deformation are essential. For this, we use a viscous model to describe the behavior of the rocks over the geological times. The viscous behavior gives us the relationship between the deviatoric stress and strain rate with a governing parameter, which is the viscosity. There are simple solutions to channelized flow problem. They involve the solution of the force balance under a given set of boundary conditions, and these are the Couette and the Poiseuille flow models, which we discussed in this lecture. The rock creep is temperature and strain rate dependent. For this, we've discussed the use of power law models. And there are different deformation mechanisms and also elasticity. Sometimes we want to combine with viscous creep. And for this, we need to use a combined creep model based on Maxwell model. And yes, in general, the rock should be also elastic, and this is why we derive viscoelastic models. So, thanks for your attention.